So, hello students. In the previous class, we had seen three different types of isoparametric calculations. So, one is the estimation of the stiffness matrix, and the other is the load vector due to the body weight, and then the load vector due to the stresses B transpose sigma. And in this class, let us look at how we can calculate the force vector due to surface pressure. And the equation for this is integral n transpose T ds, and this is a surface integral, whereas the previous ones are all volume integrals. This is a surface integral, and in a two dimensional case, we have surface means length multiplied by width, and so we have only integration in one direction and then multiplied by either the thickness or a unit value or radius, because in the case of axisymmetric, and so here it is n transpose T, and our T is the traction vector, J is the Jacobian determinant d xi, and then the factor is the thickness for plane stress and 1 for the plane strain, and then the radius for axisymmetric case. And this traction is, there could be a normal traction or a shear traction. So, let us look at the surface pressure acting on an 8 node element, and this we can treat it as a line element with some thickness or unit thickness, and n1 we have already derived them in the context of one dimensional isoparametric elements. N1 is xi times xi plus 1 by 2, n2 is xi times xi minus 1 by 2, and n3 is 1 minus xi square. And our equation is n transpose T ds, and initially we will do simple calculations, and then we will not assume any direction for these forces, except that we know. So, if there is a normal pressure acting on this surface, it is in the negative y direction, or if it is acting on this side, it is in the along the x direction, and so on. But we will later we will see how to automate them, because we humans, we have the brains, and we can say that this is a horizontal surface, and then we have vertical pressure. But then how do you make a computer know that this is a horizontal surface and this force should be acting in the negative y direction? That we will see later. And our shape function matrix will be n1 0, n2 0, n3 0, because we have only 3 nodes, and then the traction is Tn and Ts. The Tn is the normal pressure on the surface, and Ts is the tangential pressure on the surface. Sorry, I think this should be xi, but somehow because of incompatibility between different computers this happens, but I will correct it later. So, our normal force at node 1 is n1 times Tn, and then the Jacobian at different xi's, and the integrated over minus 1 to plus 1, and in general the traction at any point could be written as n1 Tn1 plus n2 Tn2 plus n3 Tn3, where Tn1 is the magnitude of the normal traction at node 1, Tn2 is the magnitude of the normal traction at node 2, and this is at node 3, and this is an input parameter. This we have to give as an input, as a data, and so our n1 is xi times xi plus 1 by 2, n2 is xi times xi minus 1 by 2, N3 is 1 minus xi square, and the determinant of the Jacobian matrix is just simply dou x by dou xi, because we have only one coordinate xi, and then this being a horizontal surface, there is no dou y by dou xi, it will be 0. Okay. So, our dou x by dou xi comes out as L by 2, because the center node is exactly at the mid length. So, the xi's cancel out, and then we are left with only the L by 2. If this is the length L, dou x by dou xi is L by 2, and the load at node 1 is N1 times Q. Q is the normal traction acting on that surface, d xi, times mod j, determinant is L by 2 multiplied by unit thickness. So, P1 is QL by 6, and then P2 is also QL by 6 if you do this integration. Then P3 is 1 minus xi square, that is the shape function Q d xi L by 2 times 1, and this comes out as 4 QL by 6. We see that at the two corner nodes the load is QL by 6, whereas at the center node, at the mid side node, it is 4 QL by 6. It is 4 times the load at the two corner nodes, and a similar response we have also seen when we calculated N transpose B or B transpose sigma. Always the mid side node, they have higher contribution compared to the corner nodes, and then the center node, it might have much higher contribution, and if you add up P1 plus P2 plus P3, it comes to QL, and we are considering unit length in the perpendicular direction, because this is a plane strain case. So, it is just simply QL, and this surface could also be a part of a 6 node triangle. It need not be of 8 node quadrilateral or a 9 node quadrilateral. And we can do the same thing even with the numerical integration. See, previously we have done the analytical integration, but now let us do with a numerical integration. Let us use a 2-point integration, because we have a second order polynomial. So, if you go through this product and use the brackets correctly, you will get QL by 6, that is the P2, and then at the mid side node we get 4 QL by 6. Like if you go through this entire thing and then simplify, we will get 4 QL by 6, that is the same as what we got analytically. And now let us look at an axisymmetric surface, and the only difference between the plane strain and axisymmetric is the radius. So, in the plane strain case we have a unit thickness, but in the case of axisymmetric we have the radius that is varying along the length, okay, along xi, okay, and our N1 is xi times xi plus 1 by 2, N2 is xi times xi minus 1 by 2, and N3 is this, and our radius can be written as 1 in general N1 R1 plus N2 R2 plus N3 R3, and that comes out as 1 plus xi R by 2. So, when xi is minus 1, we are at this point node 2, that is 0, and at xi of plus 1, you have at node 1, that is R, 1 plus 1 by 2 times R. Then at the mid side node xi is 0, so that is R by 2. Okay. So, dou R by dou xi comes out as R by 2, just as how we got as L by 2 for the plane strain case, we will get the same thing, R by 2, and the load at node 1 is P1 is QR square by 6, and P2 it is coming out as 0, and P3 is QR square by 3. QR square by 3, and so we have 3 nodes, node 1, node 2 and node 3. At node 2 there is no load. Actually you can imagine this is a circle, and the center point is the point of center of gravity, and so it should not attract any load, whereas the other nodes are attracting load, and the mid side node is attracting higher load compared to the outside node, and the total applied load is the Q times surface area, and we are considering only unit radian. See, pi r square is the total area of the circle multiplied by Q divided by 2 pi is our applied load, Q r square by 2, and our P1 plus P2 plus P3 is also Q r square by 2. So our calculations at the different nodes are correct, like if you compare with the total applied load. And we can also apply our numerical integration, and our polynomial order is of 3. So our r is at any xi is r times 1 plus xi by 2, and since we have a third order polynomial, we can use 2-point integration, and then we get exactly the same as what we got analytically, Q r square by 3. And the surface pressure on 3-node triangles or 4-node quadrilaterals are much simpler. We can follow the same procedure, and we will get equal load at these 2 nodes, QL by 2, QL by 2, and the total load is QL, because our unit we are considering a unit thickness in the outer plane direction. Then we could apply our numerical integration procedure for any distribution, like our Q need not be constant. Let us say we have a triangular distribution like this. Q is Q naught at xi of plus 1, 0 at xi of minus 1, and then Q by 2 at node 3. The Q at any xi can be written as 1 plus xi times Q naught by 2, and we can use this Q in our equation, and then do the integration either by analytically or by numerical integration. Then we can get the solution. Okay. And so if you have a situation like let us say you have 2 elements A and B, and what we do is we calculate the nodal forces separately on each of these elements. Element A we are going to calculate, and element B we are going to calculate separately and then assemble. And this particular node is common for both element A and element B. So the force at this node is going to get added up from element A and B, whereas for other nodes it just simply the load from its own element. Just as how we are assembling the stiffness matrices, we have to also assemble the load vectors. See, till now we considered only plane surfaces, planar surfaces, but then let us say we have a thick cylinder subjected to internal pressure. So now our surface is not a planar surface, it is a curved surface, because it is a complicated shape. And how do we deal with it? So for that we need to completely change our approach, because till now we considered only a single surface, but then we may have a situation where our slope itself is changing, like instead of being horizontal or vertical, we could have a curved surface. And before we generalize, let's do the calculations for a simple two cases like this. Let's take an inclined case like this, wherein our surface is inclined at an angle of alpha, okay, and we have node 1 and node 2, and once again we number in the anti-clockwise direction. Node 1 is x1 y1, node 2 has coordinates x2 y2, and dou x by dou xi is x1 minus x2 by 2, and dou y by dou xi is y1 minus y2 by 2, and the length of this element we can get as this dou x by dou xi whole square plus dou y by dou xi whole square, this whole thing under root, and this is L by 2, and that is j. And what is dou x by dou xi? It is x1 minus x2. So we can write that as this Jacobian determinant multiplied by cosine alpha, whereas dou y by dou xi is y1 minus y2 by 2, that is the vertical component. So we can write this diagonal length multiplied by sine alpha. The diagonal length is our j, and our dou y by dou xi is mod j times sine alpha. And actually our dou x by dou xi and dou y by dou xi, they are not only giving us the determinant of the Jacobian, but also the direction cosines, cosine alpha, sine alpha, as we can see here, okay, represent the direction cosines. We can use them for resolving our applied forces in different directions. And so if you have any surface like this, element node 1, node 2 and node 3, and let's take the positive normal component as a pressure acting into the surface. So we need to have a consistent scheme so that we can program them easily, and the consistent scheme is anti-clockwise numbering, and then the normal pressure acting into the surface, and then the shear force or the shear stress acting from node 1 towards node 2. So the Qn is positive acting into the surface, and Qt is positive acting from node 1 to node 2, and if that is so, we can write the x component, x direction component, as the Qn times sine alpha minus Qt times cosine alpha. So the force, normal force multiplied by sine alpha minus tangent force multiplied by cosine alpha. Similarly, y direction component is minus Qn times cosine alpha minus Qt sine alpha. Basically, we are just resolving them, this Q normal and Qt, by using the trigonometry into x and y directions, while our x and y are the coordinate directions, and Qn and Qt, they refer to the element surface. So by combining the whole thing, we can write our load at any node like this Px in terms of our sine and cosine terms, because our sine and cosine are related to the dou x by dou xi, dou y by dou xi, like this. So we can write using our derivatives of x and y with respect to xi, okay, and this is our x component, this minus this, like here you see the Qn sine alpha minus Qt cosine alpha. and sine alpha is with dou y by dou xi term, okay. Cosine alpha is with dou x by dou xi term, okay. And similarly py, that is minus of this cosine alpha term and minus of this sine alpha term, the qn and qt. So, if you apply these relations, we should be able to take care of any curved surface, because at any curved surface the tangent direction is changing. At different xi you get a different tangent, and automatically our dou x by dou xi, dou y by dou xi, if you evaluate them at that point, you will automatically take care of this tangent. Then with these equations we can directly distribute them into the correct directions, whether it is positive x or positive y, and negative x or negative y, okay. And just one small example, let us take an element like this 1, 2 and 3 at an angle of 30 degrees, and the length the coordinates are defined like this: node 1, node 2 and node 3, and the length is 10 meters. And if you calculate dou x by dou xi, you get 4.33, that is cosine 30 times L by 2. L by 2 is 5 times cosine 30 is 4.33, and 5 is the mod j for the dou x by dou xi, okay. The j L by 2, okay. And similarly dy by dou y by dou xi is 2.5, that is sin 30 times mod j, okay, sin theta times mod j, and then our mod j is square root of dou x by dou xi whole square plus dou y by dou xi whole square, okay. So, so we can easily apply these equations that we have here to directly calculate our forces in different coordinate directions. So, these are all different numerical examples that you can follow, and then if we implement this algorithm into the computer program, it can automatically take care of our pressure acting in different directions. Like if you see the circular surface, see the pressure value is the same, but then its component is acting in different directions. At this point it is acting vertically up, whereas at this point it is acting horizontal to the right hand side, and here it is acting down, whereas here it is acting horizontally to the left side. And our cosine alpha and sine alpha terms, they help us in automatically doing these calculations without resorting to anything. And the systematically we have to be consistent, and our consistent notation is our node numbering is in the anti-clockwise direction 1, 2, 3, and then the normal force is normal to the surface, tangential force is acting from node 1 to node 2. So, as long as you do that, you will get the correct x and y directions. So, I think that's the end of my lecture, and if you have any questions, please send an email to my email profkrg@gmail.com. So, thank you very much.